A different way of thinking of acids and bases is the Bronsted Lowry definitions, where an acid is a proton donor. Protons are H plus ions, just like we saw. So an acid is something that has an H plus ion that is able to give away, and bases are a proton acceptor. So we then look at acid and base properties in terms of how the protons are transferred, whether they're given away or whether they're accepted. So we've got this equilibrium that can happen right here. Let's start with this one. NH3 and water will be at equilibrium with NH4 plus. So what had to happen over here in order for NH3 to become NH4 plus?
So protons move from the water molecule to the ammonium?
Yep. So here, let's draw sort of a little dashed arrow. Don't draw a real arrow because we save those for something else. But let's write H plus transfer. Right, one of those H's came from water to NH3. So what would the other product be over here?
Hydroxide.
Yeah, it would be hydroxide because water lost an H plus, so that would leave a OH minus behind. Okay, so now we can classify these two reactants based on whether they were a proton donor or a proton acceptor. So NH3, that was the acceptor, right? So we would call NH3 a base, and that would make water the acid. Okay. Specifically because of how that proton transfer happened. Okay? And that would be the end of it if it was just a forward arrow. Okay? But this is an equilibrium. When we have those two products, the reverse reaction can also happen. Okay? So let's think of the proton transfer that would happen to make the reverse reaction. What would we have to do in order for these things to go back to NH3 and water? Yeah, you'd have to do that kind of proton transfer. Okay, and in that case, over here on the right, NH4 plus would be considered the what? That is the acid, and hydroxide is the base. Makes sense that hydroxide acts as a base. Okay. All right, so when this proton transfer happens, we have two pairs of substances that are just one H plus apart. In other words, NH3 is related to NH4 plus by a proton, right? Okay. So we call those conjugates of each other. Conjugate, just only different by one proton. Okay. And we call it a conjugate blank based on what it behaves as. Okay. So if we said, let's write it this way, that NH4 plus is the conjugate blank of NH3. It is the conjugate acid of NH3. Okay? If we reverse that, NH3 would be the conjugate what? Base of NH4 plus. Okay? Wouldn't hurt for us to write that. NH3 is the conjugate, I'm going to just do CONJ, conjugate base of NH4 plus. Okay? And together, NH4 plus and NH3 are a conjugate acid-base pair. Okay? That makes sense? So in an acid-base reaction where we've just transferred a proton, we can talk about conjugates that way. Okay? And it shouldn't be too difficult if I give you one of the products there. What's the other product going to be in this equilibrium?
H3O?
Yep, it's going to be H3O plus. So what was HF acting as here?
Acid.
Yeah. So it goes acid. The thing it reacts with, the thing an acid reacts with has to be a base, right, if it was a proton transfer. Okay. What was an acid over here, right, HF, if we lose an H plus from the acid, this will automatically be considered a what? Base. Yep. Because the reverse reaction will have it accepting that same proton that it lost as an acid. Right? Okay. What do you notice about H2O in these two reactions?
It can be either acid or base.
Yep. Depending on what the other substance is that's next to it. Depending on whether the substance that's nearby it would rather accept a proton or whether that substance would rather donate a proton. Okay? And that comes from energetic stability. We'll talk about that a bit more later on. Okay? But there are reasons why why we do this instead of that becoming HF2 plus and OH minus. There are energetic reasons for that, and we'll start to make some connections with that as we go along. But for now, it's just a matter of identification, okay, based on what happened, okay, based on tracking that proton through, identifying that certain things like water could go either way. Okay. It has H's to be lost. It also has room to accept an additional H, okay, that way. So these are, let's do a little bit thinking about conjugate acid-base pairs. Just asking a question about a substance then. Okay? There are other substances that can go both directions. HSO4 minus is one of them. What would be the conjugate acid of HSO4 minus? If I want to know what the conjugate acid is, do I have to add an H plus or remove an H plus from that? We would have to add one in order to make an acid, right? Once we have that acid would be able to give away that H that it just got. So let's write this. The conjugate acid of HSO4 minus is H2SO4 with no charge, right? Because if this acted as an acid, what did we say that acids do on this page? They donate a proton. If this acid donated a proton, we would end up with HSO4 minus. See how that works? Okay. So, what would be the conjugate base of HSO4 minus? SO4. 2 minus. Okay. Okay. So, over here, let's write the little explanation. This acid could donate an H plus to become HSO4 minus. Sulfate could accept an H plus. Okay. So, if you're ever asked, what is the conjugate acid of this thing, what do you just need to do to its formula? Yeah. If you're asked, what is the conjugate acid, all you have to do is add H plus, right? That will turn that into an acid because it now has an extra H plus which it's able to get rid of. That's what acids do. Okay? When you're asked what is the conjugate base of something, what do? Yeah, you remove. Okay. So the conjugate acid will always be more positive, right, because it has an additional plus charge to it. The conjugate base will always be more negative. Okay? That doesn't mean that it's always positive or negative. It's a scale, right, relatively speaking, more positive and more negative. Okay? It doesn't matter where along that scale it is, because we're just adding or removing H plus ions. Okay? So make sure you get that straight. What do you suppose this definition is? Yeah. Amphoteric?
That's if something can act as either an acid or a base.
Yep. If I were a little better with my dead languages, I would be able to break that apart into its roots for you. But yeah, so.
You're not one of the 150 people that are fluent.
I can count to 10 in Latin. It's better than nothing. All right. So, there are two amphoteric substances on this page. Right? What's one of them?
Water.
Water. Water is a classic amphoteric substance. HSO4 minus is an amphoteric substance. Basically, anything, if we started with H2SO4, it has multiple acidic hydrogens. Okay? So we can actually sort of think of it, let's draw it like this. H2SO4, HSO4 minus, SO4 2 minus. Okay? You can have that sort of string of one by one removing H pluses from acids. Okay? That is a diprotic acid. In other words, it has two hydrogens that can be donated. So typically, if you're anywhere in the intermediate levels of that, it's an amphoteric substance because you could go in either direction. Okay? So diprotic, there are triprotic acids we'll talk about later on. So anywhere on that, anywhere in between the extremes of that scale, you have an amphoteric substance. Okay? But that's going to be important for us later on. Okay.